Shapes of molecules, Mr. Nickel, and my name is Matt Action.
Okay, thanks for the introduction, Matt. We are going to look at shapes of molecules today. This is our last thing we really need to look at to be able to justify polarity. I'm going to give a wee introduction about polarity in this as well, but the key thing we're looking at is how we use the Lewis structures that we have to determine how many regions of electron density we have, and then from that, how many bonding atoms, so what shapes have we got. So I'm going to use these contexts here to help show that. So first one's CO2, and if we draw the Lewis structure for that, so we've got 4 valence electrons for carbon, 6 from each of the oxygens, means a total of 16 electrons. So we should have, when we draw it, carbon double bound to each oxygen, and then they have lone pairs of electrons on each end. When we're describing the shape, we always look at the central atom. And if we have a look there, even though there are 4 chemical bonds there, there are actually 2 double bonds. So we've only got 2 regions of electron density. Now there's a thing called the VSEPR theory, which says basically that regions of electron density, so bonds and lone pairs of electrons, will try to get as far away from each other as they possibly can. So the easiest way for these 2 regions of electron density to get far apart is to be either side of that nucleus. So their negative charges are sort of buffered by the positive nucleus of the carbon. So you'd expect this to be a 180-degree angle, and it is. So the way we normally draw this is like that to show the actual shape. Or we could actually do it just as circles to represent the different atoms, and maybe colour the central one in. The name we give this is really easy. If it's 180 degrees, we call it straight or linear. So really easy words. But you do need to know the angle. So we've got 180 degrees here, and we call it linear. Or as I say, straight would be fine. Okay. So if we've got 2 atoms, it'll always be linear as well, no matter how many regions of electron density. Because if you've got only 2 atoms, there can't be another angle. It just has to be straight. So that's why I haven't shown this one up here. Our next one, CH2O, which is an organic compound, has got carbon in the middle as well. And we find that it has got a Lewis structure that looks like that. Now if I have a look here, yes, my carbon's got its 8 electrons around it, and so does my oxygen. Okay, remember each line is with 2 electrons, because you need 2 electrons to make a chemical bond. So I look here and I've got 1, 2, 3 regions of electron density. Now again, the easiest way to get 3 regions as far away from each other as possible is to lie them on a plane and put them at the apices, or the corners, of an equilateral triangle. So I'm going to try and draw this one again, and this is always one I'm really bad at, where my coloured in one is carbon. Okay, now I haven't shown the double bond. My lines here are only representing regions of electron density. So if I was good enough at drawing these, we would find that the angle here would be 120 degrees. Now the electronegativity and all that of certain atoms does change that, but you don't learn about that until next year. So whenever you've got 3 regions of electron density, you get them sitting flat on a plane, and they are the apices of a triangle, so you'll find the angle is 120. Not surprisingly then, the name of this is triangular planar. Now you can't just say triangular, because that doesn't really work. Okay, you have to say that it's lying on a plane. Right, our next 3 are our sort of harder ones. Let's move the sulfur dioxide over a little. And these sort of show what happens when you, well, these two show what happens when you don't have every electron cloud filled up. This one here though, we did this yesterday as well, and we found that its Lewis structure looked like this. Now, some people had the chlorines and the hydrogens in different places. That's okay, it's not important. You could even put them opposite and it would still make the correct diagram when we do it. Now for these 1, 2, 3, 4 electron clouds to be as far away from each other, you can't do that in only 2 dimensions. You need to go into 3 dimensions here. So you need depth. Problem is I'm writing on a flat surface, and so will you be when it comes to an exam. So how do we show 3 dimensions? Again, I'm going to colour in a circle to show carbon. There's 2 ways to do this. I'm going to show both of them. And both are equally correct. We have one of those bonding atoms flat on the page going straight up. Now the way that I prefer to do it, because it becomes easier for learning about organic chemistry and things called optical isomers, is this way. I have a triangle going like that, which shows an atom coming slightly out of the board on that angle. So it's coming out towards us. I have it there, and I have it there. Then I've got one that disappears into the board a little bit. So I do a whole set of parallel lines that diminish, so come down to basically a dot. That shows one straight behind that goes into the board. And it doesn't matter which way I arrange these atoms, so I'm just going to do circles for this one. Okay. This is a 4-sided 3-dimensional structure, and all of the angles are the same. They're 109.5 degrees. This has got a special name. It's called a tetrahedron. So the shape we describe as tetrahedral. Now the way you'll see it drawn in your book is a little bit different, and I'm happy with either. They have one straight up and down there, then one out on an angle there, then they often have one diminishing and one coming out here. That's just them rotating my one a little bit. Alright, so that's all it is. We're just looking at them from different angles. There's no actual difference in the 2 diagrams at all. Sorry, I better put my hydrogen, my circles to represent the other atoms, hydrogens and chlorines. So that's all pretty easy so far. This is where we've got the number of bonding atoms are equal to the number of electron clouds, or regions of electron density. What happens if they don't? Well, ammonia is a really good example of this. Ammonia's Lewis structure shows us one lone pair of electrons at the top. So I still have got 1, 2, 3, 4 regions of electron density. So this time my coloured in one is going to be nitrogen. So I still draw the same diagram. Now I do this in pencil if I'm doing it in a test, because I'm going to rub something out. My lone pair of electrons up here are not contributing to the shape, but they are contributing to a repulsion of the hydrogens. So I'm going to get rid of that line so I don't confuse myself and call it tetrahedral. That's why I've used my pencil. So I'm going to get rid of that line on the top, and I'll put the lone pair of electrons a little bit closer together. Now this is created like a triangle where I've pulled the middle up in the middle, and that's the nitrogen. So we call this shape a trigonal pyramid. So to describe the shape, it's trigonal pyramidal. It's probably the hardest one to remember. Okay, it's trigonal, a bit like this one here, which you can also call trigonal planar, by the way. So trigonal, 3 sides. Pyramidal, because it looks like a pyramid. But a pyramid has 4 sides, just in case you're unsure of the difference. An actual pyramid has got 4 sides. It doesn't have 3. Alright? So this is an example where I've got 4 regions of electron density, so therefore a tetrahedral electron cloud. But I only have 3 atoms bound to the central atom, so therefore it's trigonal pyramidal. And that's the way I'd describe it, of having to explain the shape. Now this is also going to be a polar molecule because the nitrogen-hydrogen bonds are polar, so there is a pull towards the nitrogen on every set of bonding electrons, which will therefore make this side of the molecule delta minus, and the bottom of the molecule, as well as the hydrogen side, will be delta plus. So you can hopefully see how we use Lewis structures and shapes to help work out polarity. But we'll do that in more depth tomorrow. The last one is sulfur dioxide, which is probably one of the ones that examiners seem to like the most. Sulfur dioxide, trust me on this, you can work it out later if you have to, has got this Lewis structure. So it's got 3 regions of electron density around the central atom. 1 for the bond, 2 for the lone pair, and then the third one is the double bond. Remember, the fact that it's a double bond, it's still only 1 region of electron density. Alright, so in your little models that you're going to make, 1 toothpick would represent this. So 3 regions means that it has to have a trigonal or triangular planar electron cloud. 3 regions of electron density. So I do my sulfur, and then I do my 3 lines coming off it at roughly 120 degrees. Then I put in my oxygens, and that one there is my lone pair of electrons, so let's put those in there. If you have a look, that lone pair is pushing those oxygens near each other. So it's no longer linear like we had up here with CO2. SO2 has got about a 120 degree angle here. So therefore, it's got to have a different name. And it's got one of the easiest names to remember actually. If you tip it up, it looks like the letter V, so it can be called V-shaped. Or, if you want to be really simplistic about it and equally correct, if that one's linear, then this one must be bent. And it's that simple. Don't go calling that one straight and that one something else. But linear and bent. Alright? So those are your basic shapes that you have to know. You will find that there are bent ones which have 4 regions of electron density as well. Okay? So if I didn't have that hydrogen, you can see that makes a bent shape there. Water is the best example of that one. You'll find some really good explanations, some very good examples in your book, so do use those as well. Right, thank you.